guess it's on. So today they solve another 3 legal questions. Man, I was intending to do 5 questions per day, but I realized it takes a lot of time, and I also need to have some time to reply to the emails, and search for the jobs, and also I haven't done much of replying. I don't know. I feel like it's really need to be very disciplined, which is like you will have to have a good eating habits, good sleeping schedules. So it's like a marathon. So I think I should do a better job on that, because right now I think I slept only for like 5 or 6 hours, and I can already see that my brain, like, it's stopped. Like the efficiency is super low. So I probably have to go to bed early today, and yeah, wish me luck. So today I solved 3 more questions. The first one is the balanced binary tree. So it gives you a binary tree and asks you should return true if the tree is balanced, which means like for every side, the height, it cannot have like a difference over 2. So for example, this node, it has 0 left, 0 right, so it's balanced, this node. And this node, the left has height of 1, and the left has height of 1, and right has height of 2 in this case. So this node is balanced. And also this node is also 1, 1, so it's balanced. 0, 0, 0, 0, so it's balanced. So this tree is balanced. So what would I think I would approach by calling a recursive call on the DFS, and we goes to the bottom, and we would check like at every node if the current node is balanced, and so we would at each node we would have a variable. It's called true. If it's balanced, then we return true, and also the current height of this node, which means like what's the height of this node. So for example, if we take this node, for example, the height if we took this node, for example, the height would be 1, because the left is 1, right is 1. So the height for this node is just 1, and for this node the height would be 2. So let's say if we have another, so we can compare their height. So as long as their height is less than the height difference is less than 1, less than or equal to 1, means it's balanced, and if not, then it's not balanced. So so as I mentioned, I would write call it maybe a DFS, so and the node, in this case, right? And if node means we can return true, and 0 in this case, and we would call the left tree is equal to self.dfs node.left right self.dfs right, would be the left. So if it's balanced means like, so for every node we need to check if the left is balanced or the right is balanced, because both of them they have to be balanced so we can return to our previous node. So so it should be index 0 and height of index 0, and we should have their height difference between the left and the right should be less than less than 1. So this is our balance, and we can return balanced. And how would be the height, which would be the 1 plus max of left and left 1 and right 1, because this is our base case, right? So in order to get the height, the current height, we should get the index 1, and also we want to get only the maximum. So let's say if we have another 8 in here, then this node height would be 2. Oh wait. Alright, anyways. So it activates my Siri. Scares me. So what would be the... Yeah, I think this should be the... And for also when we return from each node to our previous node, each iteration we increment by 1. This is a pretty standard the height increment. So yeah. So we have these balanced, and the other is the height, right? Alright, and this, and in here we can, like that is balanced, we just call our self dot bls, pass in the root node, and we can just return the first. We can just return this if it's balanced, right? So yeah. Left? Did I? No dot left. No dot right. Else. I am not sure if this is the issue. Probably not. Did I here is interesting. Or did I just spell something wrong? Oh, I see. So if not, so yeah. So if it reached to the end, we return. So it's not null means the pointer reached to the end. So we return true, and we went back. Base case. Okay, and the other question is the diameter of binary tree. So this question asks you to return what's the maximum edges between two nodes. So for this case, it's like 1, 2, 3. So it has 3 edges. So this question we would use the similar concept. We would use Leetcode depth search, and we just iterate through to the end, and we just went back. We just from bottom up, and we just increment 1, and the diameter would be just be 1 plus the maximum of left or right, which is the current maximum diameter. So so we need to have a variable self max diameter. We can say it's equal to 0 at the beginning, and also we would call a depth search function as usual. So no, we will have to see our base case. So our base case is also if now no means we can just return just return 0, and so we would also have the left is equal to DFS node dot left right, so DFS right. Don't forget you have to use the self function. And also in here we have to update our maximum diameter in this case. So max D would be max D. What would be the current the diameter? It would be the left plus right? Because if you see how would be the max diameter for this point would be left plus right, which is 0 and 0. So how would be the maximum diameter for this node is 1 and 1, right? So we only need to have left and right? But how do we increment our? I think the maximum is the current node of the maximum diameter is left plus right. So for example, for this one, the maximum is left plus right. So it's 1 and 1. Then we will have to return 1 plus left plus right. So that's where since we go up 1, so we have to increment by 1, right? This is we have to because we need to whenever we return, let's say if we return from this node, we want to get the maximum of the maximum height would be it should be return the height of the current node. Okay. And this should be update the and after all this, we just go return DFS roots. We have to code this, but we have to return self diameter or max D. Okay, let's run this. Okay, so I think here is update the diameter, and this is just return the current height of the node. So yeah, because the height here is how you calculate the height, right? I remember I did a question yesterday, and I couldn't even remember now. I don't know. I feel like am I wasting my time? Or yeah, maximum depth of binary tree, right? So this is how you get the height, right? But it's also a little bit different because it's Yu-Code. It's left. Probably I should do this, right? This one, right? Would be this one. Just I think this way. I think this way is easier, right? Because did I forget something? Really see text, of course. So here is how you calculate the depth for each node, and you just return it back to the previous node, but it's starting from the left, so it should be from the left. It keeps going up by adding up by 1, and the depth is just you have to check the left and right. What's the current maximum depth? So with this, and we can go to here, right? Because here is the same, but the only difference is we have to also update our maximum diameter in here, and the rest is very similar. And then the balanced binary tree, this one is also we have a base case, and we have the condition to check its balance. We should go like this. Yeah, so if its balance has to be checked if the first condition is true, the second condition means the left node, the left bench and the right bench, they are all balanced, because if any of them is false, means the tree is not the balanced tree, then it should keep being false. So this condition has to be satisfied, and this is the height difference should be less than or equal to 1. And we just keep returning what's the current height, and if it's balanced. So all of them, they have this, right? And also this one. So you can see some pattern there, but it's hard to come up with if you never done this question before, but once you've done this, I think it's pretty, I would not say straightforward. It still needs some memorization. Like you have to know, you have to do the left and right, and and you have to do it like bottom up basically. So instead of doing the top down, which gives you n squared of runtime, from the bottom up, we only have big O of n runtime in this case. Alright, the next one is the famous LRU cache. So this question is pretty long. And I did watch a video yesterday, and I don't know if I want to explain this question. So basically, it asks you to implement the LRU cache, and you have to implement this function with the get and put runs in all of one time. So which is usually means you can use like a dictionary hash map, or maybe a linked list, so you can get and put. But linked list for the get is hard to get all one because you don't know where's the key, and to put, you don't know. The linked list can do it in all of one time, but it's very hard. But it's not like we also have to track what's the last used unit. So is it called last? How is it called? Like list, lastly recent use. Okay, lastly recent use. Okay, so whenever we get, we should move that node to the right, and we will swap it. Basically, we'll move that node. We will remove that node, and we add it to the row, to the linked list. So we will have a hash map plus a two-way linked list. So that is what we are trying to do today. So we can visualize tags. Node. Pass So the node should be, we should have a key, and we should have a value. So we should have self.key is equal to key, self.value, val is equal to value, and self.next is equal to none, self.brief is equal to none. So that's where we have our base node structure. And for the LRU cache, you would have self.cache is equal to dictionary, and self capacity would be capacity. They would initialize two nodes, and we would count them. So we would initialize node. So self them first. So self.head.next would be self.tail, self.tail.pre would be self.head, right? So that way it's connected together. Okay, so let's work on the two functions. So before we get into this function, we need to have some help function, which is remove self, and we can have node object, right? And then we would have insert self and no in this case. So for the remove, let's say we can say p would equal to self dot. So if we want to remove, we always want to remove what's the current node, the previous node. So we need to start from the left, the node left. We want to copy. So for example, we would probably have node A, and it has D in this case, and also it also maybe have another pointer that is also pointing towards, and we might have a no. Let's put it this way. So here is the P, right? And so P, and we want to remove these pointers, so P dot next would be no dot next, right? So it's pointing to from P to here, and also we need to change this one node and pointing back to P, right? So we can get rid of this. So node dot next dot 3 would be P in this case, right? So this is our remove function. So P now points to B, and B is now pointing back to P. So this node is getting removed. Alright, and what's the insert function doing? So for the insert, for the insert, we need to always put on the right, which is the last recent unit. So we would also have P, and that can be started from self dot tail. So that way it's the node that is so that way it's inserting to the tail, right? Because we every time want to insert it in the tail, so it has to be tail.brief. And so right now it should be node A. Maybe I should just code it head, right? there's some node whatever, and we have a node here, and we want to get the tail. In this case, this tail like this. So right now here is the node, and we want to I think we can just do this. Let's imagine we don't have any node between the head and tail, and we want to insert the tail now. So self.tail.brief equals to p. So now p is in here, okay? And we can keep the next would be equals to node. Right, so we assign the node to here now, and we also want to set the node dot next would be self dot tail. So that way it's also connecting to this one, and self dot brief dot self.tail.brief would be equals to node, and the last one would be node.brief would equals to p, right? I think seems reasonable. Hope this is correct. If not, I don't know. Right. So let's continue to work on the get function. So for the get function, so if key in self.cache so if it's not in this one, we should return -1. And else if it's in the list, so the end would be self.cache key right, and we should self.remove this node, and self.insert this node, and we just return in that value. So this one we update, we remove the insert, we move the node to the right. Okay. And the last one is the put function. So if so no matter what, when we are putting the function, we are going to have I think we also need to do it. I think right now is fine. So for the put function, we definitely need to we have to first check if it's in the list or if it's not in the list, right? So if it's not in the, if k not in self.cache, right? So if this is the case, we can just append it, but also we need to check wait, I think we need to check. So if it's in the cache, then we need to have self dot what's the node? The node will be self dot cache dot key. This is the node, and we need to insert it, right? Insert. I think we can do the same. Right, we just need to remove, insert. And else if so if it's not in the cache, and also we need to check the length. If the length is greater than if the capacity has been exceeded, so the length of self.cache has greater or equals to self.cache, right? If this is, I think it's less than equals to cap. If it's the case, we can just also insert it, so we can oh wait, I think we need to, if it's the same, that means we need to kick off certain things. So self.remove what's the leftist, which means the self.have.next. This node needs to be removed, and also we need to delete self.cache what's the current, not the current key. It should be, damn, this is hard. Key, right? I think we can have initialize a node here. I don't think I can finish this in a real interview setting. So update the value if it exists. Otherwise, add a pair value to the cache. And if the number exceeds, evict the last one. So this is the evict. So if it exists, I think we can, because then we also need to do something like I think we need to create a node here. So what will be the key value? In this case, self dot cache.
One of our friends yesterday, and her dad did she say anything about me? I don't know why she followed me.
Wait, so
No, you were with me when she followed me.
here as well,
Remember, I should have.
because
I forgot about that. It was a while ago, like last year, when we were at Waterford. She randomly followed me. Huh?
yeah, because if it's in it, we would add it back. So cache.
She followed me.
Okay, so it should be like this. Then also we need to insert the node. Right, so evict the right the node next to add. And delete. This is delete dictionary, and no matter what we would put the node to the left, to the right, yeah, or to the before. Okay. So if it's in this one, we need to delete it. So because we want to shift our node to right or tail. Okay. I think that should be it. No. Where did that? Self. Something like this.
I've never been to baseball.
No. Ah. Am I did something stupid? Could be. Three given. Oh. What I have done. Yep. All right. Okay, so this is the LRU cache. This is something I think the put, especially here, the condition here and here is very tricky. And also you kind of have to know to use a double linked list and the hash map. So and you link you point the key and the value. The value will be the pointer to the linked list. So to the node, and you have like a head and tail to track what is the last used one and what is the least used one. So yeah, let's submit it. Okay, so I guess that's it for today. I'm sorry guys, I'm not recently I think how to say that, like my mental health, I don't know if it's normal. Okay, I guess nobody is watching. That's good. Alright, peace guys.